So, do you have any doubts in the previous class? Do you have any questions? Do you have any questions in the last class?
So this is an expression for both FTP and replacement mass time. ID equal to IDSS into 1 minus VGS by VP whole square. So this is for enhancement MOSFET. ID equal to K into VGS minus VT whole square. VT is what? Threshold voltage. K is constant. Okay.
So,
you know that IC equal to
made some correction in the previous class. This x2 is equal to x1 minus beta 1 u know. You get x dot 1 is equal to x2 plus beta 1 u. Right. So here your state variable must be dot here. Your assumption must be dot. You make a correction, it should be a dot. That is differentiation. Okay. So that's how you'll get the dot equations, right? These ones. So make a correction for this state variables. Right. So let us look at the last topic of the 5th unit. I hope you understood all these concepts. So we started with the state variables, state model of the LTI system. Then we have state space representation by physical variables, phase variables. Again, in phase variables, we have two types. One is which involves the forcing function and its derivatives, and other one is without derivatives of the forcing function. So that's how we have represented the state space. Then let us look at the last topic in this 5th unit. So that is solution of state equations. Let me put the heading. Put the heading solution of state equations. So in that you'll get state transition matrix STM and state transition equation. Right. So you'll get these two terms. One is state transition matrix, state transition equation, right? And this solution of state equations. Right. So what's the state equation? And we know that state equations are x dot t is equal to a into x of t plus b into u of t. This is your state equation plus d into u of t. Right. So to solve this state equation, let us start with again one condition, that is unforced equation. unforced equation means without your input function. Let us find out the solution for equation without forcing function. So that is, I'll write it here. I can say it's a homogeneous state equation. So to solve the homogeneous, you can say homogeneous or unforced state equation.
arrow work indicates customer. Arrow work indicates towards you. So this is the
State
example where F
equation,
is. Okay.
right? To solve this, let us start with the equation unforced state equation. That is x dot of t would be a into x of t, comma x of 0 is x naught, right? So this is your unforced state equation. To solve this, let us consider the scalar case. Consider scalar case. Since it's a vector, first consider scalar case. So what is scalar case? It would be x, and I can write it as dx by dt is equal to, and it becomes a, and it would be x of t, and x of 0 is equal to x naught. Now what is the solution of this scalar or homogeneous equation? From the fundamentals of the equations, I can write the solution for this equation, right? Now what is the solution? Solution of this equation x of t would be e a t into x naught, right? So this can be written as 1 plus a t plus a square t square by 2 factorial plus a cube t cube by 3 factorial plus into x naught. So this is the solution for scalar case. So by analogy with the scalar case, the vector state equation has the following solution. So I can write it as by analogy with scalar case vector state equation has the solution x of t. So now I am replacing with the vector. X of t would be 1 plus a into t plus a square t square by 2 factorial plus a cube t cube by 3 factorial plus x naught, right? Where EAT, e power AT would be I plus A into T plus a square t square by 2 factorial less a cube t cube by 3 factorial less and so on. Right? Now what is A? A is n by n. A is n by n matrix. So the solution x of t can be written as solution can be written as x of t is equal to e into at x of t, right? Now look at this equation solution. The transition in state is carried out by the matrix exponential e power at. So e power at is known as the state transition matrix and is defined as pi of t is equal to e power at. So that's why we started with the solution of state equation. So now towards the transition, so transition always carried out by this e power at. So that's why it is called state transition matrix. So let me write it here. I can write it as since transition in state is carried out by the matrix exponential e power at. So this e power at is known as the state transition matrix, or simply I can say STM. So, and is denoted by pi of t. So that is pi of t is equal to e power at, which is known as state transition matrix. This is about state transition matrix. Now let us look at the solution of non-homogeneous state equation. So this is homogeneous equation, that is without forcing function. We got some solution, that is x of t is equal to e power at into x of 0. So where e power at is known as state transition matrix. So let us look at the solution of the non-homogeneous state equation. So let us look at the non-homogeneous state equation. Right? So let us write the state equation first. Non-homogeneous state equation, that is x dot of t is equal to a into x of t plus b into u of t. Right, isn't it? So your x of 0 is equal to x. That is with forcing function. Now I can rewrite this equation as x dot of t minus a into x of t is equal to b into u of t. Right. Now multiply with e power minus at both sides. I can write it as x dot of t minus a into x of t is equal to e power minus at into b into u of t. Right? Clear? Now. Now I can write this equation as d by dt of e power minus at into x of t, right? Which is equal to e power minus at into b into u of t, right? So if you do this, you will get the above equation. So now take integration both sides. Take integration both sides. That is 0 to t d by dt of e power minus at into x of t, which is equal to integral 0 to t e power minus I can put it as tau also b into u of tau t tau. Right.
Actually, further you have to apply KVL in the input rule. Okay. To find VGS, you have to apply KVL in this input rule. VGS equal to minus VGS. Here we are not getting any.
So this would be, I can write it as e power minus at into x of t 0 to t is equal to integral 0 to t e power minus a tau into b in a variable tau here. So this would be e power minus at x of t minus x of 0 would be integral 0 to t power minus a tau into b into u of tau d tau. Right. So again pre-multiplying with e power at by e power at. So this would becomes x of t would be equal to e power at into x of 0 plus integral 0 to t e power minus a tau b into u of tau d tau. Right? So this is how you get the solution for the equation, homogeneous equation. So I can write in terms of STM, state transition matrix. I can write it as x of t is equal to pi of t into x of 0 plus integral 0 to t pi of t minus tau b into u of tau d tau, right? So this is how you can find the solution of the non-homogeneous equation. Okay. So this is about solution of the homogeneous and non-homogeneous equations and definition of the state transition matrix. So let us look at the properties of STM. This is 2 marks question. Properties of STM, right? The first property, your pi of 0 is equal to I. So what is that? Pi of 0 would be e power a into 0. So that would be I here. Second property, pi inverse of t would be pi of minus t. This is your second property, that is pi inverse of t is equal to 1 by pi of t, which is equal to 1 by e power at, which is equal to e power minus at, which is equal to pi of minus t. So this is how you can prove all the properties. Property number 3 is pi of t2 minus t1 into pi of t1 minus t0 would be pi of t2 minus t0. And the fourth property, pi of t whole to the power of k is equal to pi of kt. And the last property, fifth one, pi of t1 plus t2 is equal to pi of t1 into pi of t2. Or I can write it as pi of t2 into pi of t1, right? So this is about properties of state transition matrix and properties. Right. Now let us compute the state transition matrix by Laplace transformation. So till now we did in the time domain. Let us do the same in Laplace transformation. Right? Let us do that. The same thing in the Laplace transformations. Okay. So let us put the heading computation of the STM by Laplace transformation. So again, consider an unforced system. So again, consider an unforced system. So what is that? Unforced system means it's a homogeneous equation that is without forcing function. That is homogeneous equation. So what is that? X dot of t is equal to a into x of t. So where a is the constant matrix. Now take Laplace transformation both side. Right. So what is the Laplace transformation of x dot of t? So it would be s into x of s minus x of 0 is equal to a into x of s. The same thing we are doing with the Laplace transformations. Okay. Now, so I think we can take some common matrices here. So that would be, I can write it as S I minus A and into x of S would be x of 0. Rearranging the terms, I can get this. Now what is x of s? X of s would be si minus a inverse into x of 0. Right? So this is very important expression, this one. So we always use this one to find the solution or the state transition matrix, right? This is equation number 1 here. So here I got some matrix inverse. So that inverse matrix is called pi of s. So in the time domain it is pi of t, that is state transition matrix. Now it is called pi of s, which is si minus a inverse. What is that? Which is called resolvent matrix. Resolvent matrix. Okay. So taking the inverse Laplace transformation, you will get the x of t. This is very important. Remember this matrix, resolvent matrix. In the time domain, it is called pi of t, which is equal to e power at, which is called STM, state transition matrix. Remember this part, right? Now, taking inverse Laplace transformation, take inverse Laplace transformation to equation number 1. So if you take the inverse Laplace transformation to the equation number 1, so it would be x of t is equal to L inverse of Si minus A inverse into x of 0, right? So let it be equation number 2. Now we'll compare this solution using Laplace transformation and your time domain approach and compare the values. So what are they? You have pi of t is equal to e power at and x of t is equal to e power at into x of 0. So what is the earlier equation? Earlier equation is x of t is equal to e power at into x of 0. So let it be third equation, right? Now compare these two equations. It would be pi of t is equal to e power at. We know this is a transition matrix, and this would be is equal to L inverse of Si minus A inverse. It's very important relation, which is nothing but L inverse of pi of S, which is equal to state transition matrix. So very important relation. So we use this relation to solve the problems. So what is that? Your resolvent matrix, your pi of S, is nothing but Laplace transformation of the pi of t, or your pi of t is equal to inverse Laplace transformation of your pi of S. So this is very important relationship. So I can write it this conclusion. Yeah. I can write it as STM is the inverse Laplace transform of the resolvent matrix.
Next one.
Right? So this is a very important conclusion. So let us now consider the forcing function that is non-homogeneous equation, and we will find the solution for the non-homogeneous equation by Laplace transformation method. Okay, so let us do that.
No wonder. So we have only one power supply. We are using only one power supply. That is the one of the advantage. Better than fixed power, it eliminates the need for two power supplies. And also one more difference.
So consider now consider
here only one power supply. One more difference is RS.
the forced response of the system, or x dot of t is equal to a into x of t plus b into u of t. Right? Now take Laplace transformation both sides. So what is the Laplace transformation? It would be s into x of s minus x of 0 is equal to a into x of s plus b into u of s. Right? So I can rewrite this equation as si minus a into x of s is equal to x of 0 plus b into u of s. Right? Or I can write it as x of s is equal to si minus a inverse into x of 0 plus si minus a inverse into b into u of s. So I can write it as x of s is equal to what is si minus a inverse, which is nothing but your resolvent matrix pi of s, right? I can take it as a common, or I can write it as x of 0 plus b into u of s, right? Now take inverse Laplace transformation, right? So what is inverse Laplace transformation? it would be x of t is equal to L inverse of phi of s into x of 0 plus b into u of s, right? Or I can simply write in the state transition matrix, x of t would be phi of t uh, into x of 0 plus L inverse of phi of s into b into u of s, right? So this is the solution for non-homogeneous equation, right? Or if you apply convolution theorem to this, you will get convolution apply convolution theorem. It would be x of t is equal to phi of t into x of 0 plus integral 0 to t phi of t minus tau b into e of tau d tau, right? Right. Now we have one more term called state transition equation. So this solution of linear non-homogeneous state equation is called the state transition equation. State transition equation. So this is how we have state transition equation and state transition matrix. This is the theory part behind this last topic. Here we found the solution for homogeneous equation and non-homogeneous equation, and we got few terms. One is state transition matrix STM, and one more is resolvent matrix or P of S, which is equal to same and say inverse, right? So this is the theory part of the last topic. With this, I completed the 5th unit. So let us find out the solution for one example. Okay, so let us take one example to solve this or to understand this concept. Okay, so example. The question is, obtain STM for the state model whose A matrix whose matrix is given by A is equal to 1, 1, 1, 0. So obtain the state transition matrix. So what is state transition matrix? Let us look at the state transition matrix STM. So STM is equal to your phi of t, which is equal to e power at, or which is equal to L inverse of phi of s, or I can write it as L inverse of Si minus A inverse, isn't it? This is our STM. So to find out the state transition matrix STM, I need this inverse of Si minus A. So I can find Si minus A as Si minus A would be, so it will be as 0. This is your Si minus A. A would be 1, 1, 1, 0. And this is equal to S minus 1 minus 1, and it is 0, S minus 1, right? So what is pi of s? Your resolvent matrix pi of s would be Si minus A inverse, right? So what is that? Adj by adjoint Si minus A by det A. That is Si minus A. Okay. So what is adjoint of Si minus A and determinant of Si minus A? That would be Si minus 1 whole square, that is Radiman species, and it would be S minus 1. So change and put some sign change. Okay. So this is your minus D minus A minus B and C, exchanging the elements and removing the signs. The joint of A. So is it correct? So I think we made some mistake here. Zero and 1.
So you can use this equal to minus sin x is equal to 2 into Rs.
So I can rewrite this equation as your pi of s is equal to 1 by s minus 1, 1 by s minus 1 whole square, and this would be 0, and this is 1 by s minus 1. Okay. Now, what is STM? STM is pi of t, which is L inverse of s inverse. Okay. So this is equal to L inverse of 1 by s minus 1, 1 by s minus 1 whole square, 0, 1 by s minus 1. So this is equal to, what is this? This would be e power t, and this is t into e power t. This is 0, and this is e power t. T is nothing but your pi of t. So if you have any questions, you can ask. So if you have any questions, you can ask. So if you have any questions, you can ask. So with this, I almost completed the 5th unit. I have only one topic. So we'll see that topic in the next class, which is transfer function from the state model. I will, if you want, I'll complete this topic also quickly. I think we have 10 minutes. I hope I can complete it. If you don't have any doubts, I'll complete this topic. This transfer function from the state model. So what is that? The state model is the state model is x dot of t is equal to a into x of t is b into u of t, and y of t is equal to c into x of t plus d into u of t, right? So take Laplace transformation both sides, right? So I think we did this. We got some equation for it would be s into x of s minus x of 0, which is equal to a into x of s plus b into u of s. So what's the objective? Objective is finding transfer function of the state model, that is output by input, that is y of s by u of s, isn't it? This is your transfer function. Okay. So by rewriting this, you'll get sa minus a into x of s, which is equal to x of 0 plus b into u of s, right? So I can simply write it as x of s is equal to sa minus a inverse into x of 0 plus sa minus a inverse b into u of s. This is, let us say, equation number 1. And we did this already. Now, what is the second equation? Applying Laplace transformation, it will be c into x of s plus d into u of s. Right? This is second equation. Right. Now 1 into, so your y of s would be c into si minus a inverse into x of 0 plus c into si minus a inverse into b into u of s plus d into u of s, right? So I can write it as y of s is equal to c into si minus a inverse into b plus d into u of s, right? So your y of s by u of s would be, which is nothing but your transfer function, is equal to, I can simply represent as t of s, would be c into si minus a inverse into b plus d, right? So this is your transfer from function from the state model, right? So let us quickly do the one example on this model. So example, obtain the transfer function of a system described by the state model. So that is x dot 1 of t, x dot 2 of t, x dot 3 of t is equal to, I have 0, 1, 0, 0, 0, 1, -1, -2, -3, which is x1 of t, x2 of t, x3 of t, plus 0, 0, 1, 0, 0, 1 into You have two forcing functions, u1 of t and u2 of t. And then y1 of t and y2 of t, which is equal to 1 0 0 0 0 1 x1 of t, x2 of t, x3 of t. Now, what is the transfer function? Is nothing but C matrix multiplied by Si minus A inverse into B into D. And we got all the matrices here. You just do some multiplications and you will get the answer, right? So this is your A matrix and B matrix and C matrix. There is no D matrix, right? So obviously you will get transfer function T of S would be C into Si minus A into inverse B plus D. So here I don't have any D, so I use only up to this part, right? Do this part. So it would be, I'm writing the direct value. You solve for this. You will get Si minus A inverse would be have some denominator value and the value S plus 2 into S plus 1 into S plus 3 into 1 here, sorry, S plus 3, this is 1 minus 1, S into S plus 3, S here, S square here, minus 2S plus 1 here, and this is minus S by S cube plus 3S square plus 2S plus 1, right? So now you substitute multiply with C and B, you finally get your TFS would be something like this. S plus 3 here, 1 here, minus 2S plus 1, and this is S square by S cube plus 3S square plus 2S plus 1. Right? So with this, I completed the 5th unit. So if you have any questions, you can ask. So if you don't have any questions, you can leave.